Hello everyone, welcome to recitation number 9. Today's focus is going to be a bit more on Turing machines, and then we'll talk about some decidability. Now, just a quick note, make sure you revise recitation 8 because that's where we first introduced Turing machines. And actually last time what we did was we were able to give a machine, it's a Turing machine, but it's some machine that was able to break the ceiling of PDAs, and we were finally able to solve the problem A and B and C n. If you remember, we couldn't do a PDA for this, that was the ceiling for PDAs, but all Turing machines are able to do them. And so we had now this new level on our hierarchy, the Turing machines. And essentially, these are probably the strongest layer we have. Like, Turing machines are the closest things we have to computers. They're actually like the theoretical idea of a computer. Really, anything that you can do with a computer, you are able to do with a Turing machine. Whether it's Facebook, YouTube, whatever, technically you are able to do it with a Turing machine, even though if it's not, it might not be very efficient, but it is technically feasible. So the answer to maybe our question is, what is a computer? Well, for now, the closest thing we'll just say it's a Turing machine, and we'll see how we can add on to that in the next few weeks. Now, for the Turing machines, essentially, just a quick reminder, what we have is if you want to move from one state to the other, you do that by read, write, and move. So if I want to go from Q0 to Q1, I'll read, I'll put the arrow on the right, and then I'll move. So it looks similar to maybe how the PDA, but first you write the arrow, then you write, unlike PDA where you read pop and then there's an arrow sign. So make sure you don't mix those two together. But on top of this new movement, we also mentioned we might have an infinite tape. So it could be a bunch of zeros and ones or whatever your alphabet is. So say right now I'm at Q0 and my header is pointing to this part of the tape, and I have something like, oh, read 1, write, or read 0, write 1, and move to the right. That just means, okay, I'm currently looking at this 0, I'll overwrite it with a 1, I'll move to the right. So now my header points to here, and I'm at state Q1. And depending on what state Q1 is, what outgoing transitions we have from there, we'll keep going. And again, a reminder that the states are immediate, accepting and rejecting states. So we no longer have, so now we have the accepting states are immediate. That means once you enter an accepting state, you'll accept right away. You won't then transition somewhere else. And it kind of makes sense, right? Because before you had to traverse through the whole string from left to right, and then if you ended up at an accepting state, you'll accept. But with tapes, there's no end. Like even if you reach all the way to the end of the tape, then you can move all the way back to the left to the beginning. There's really no place to stop. So hey, if you ever enter an accept state, you'll accept and stop. And same thing if you enter a reject state. You'll also just accept right away and stop. So the main three ideas that we saw last time when it comes to Turing machines are as follows. We want to be able to draw, or first let's say we want to, because usually before drawing, what you do is you give a high level description for a machine. So give a high level description. Just think of it like you're giving an algorithm for a program, like how does your program work without actually writing the code. Then you want to draw that program, you want to draw that machine. So this is like you're actually writing the code, or you're like theoretically you're drawing the Turing machine. We've seen this with PDAs, DFAs, etc. So you want to be able to draw a Turing machine. And finally, you want to be able to understand a Turing machine that's given to you. So imagine somebody wrote some code and gave it to you. You want to be able to dissect it, understand it, or somebody gave you a Turing machine that they already drew. You want to be able to understand that too. So understand a given Turing machine. And all of these ideas we saw last time. Right now we'll focus first on these first two. Ooh. So for this next problem, describe a Turing machine that decides the language L. W is made up of zeros and ones, and the number of zeros in W has to equal the number of ones. Now, we've already seen this problem before. We solved the problem for a PDA that wanted to have the same number of A's and B's. This is the exact same thing, but a different alphabet, 0 and 1. And we're doing a Turing machine. So technically, we could solve this with a PDA. PDA are strong enough, but hey, still, we're going to be doing it with a Turing machine anyway. So step 1, or first idea, let's give an algorithm for this. Of course, at any point, you can pause and think of the questions yourself. So step 1, let's give a high-level description. So I'll say I have the string 0, 0, 1, 1, 1, and then 0. Now, usually you could assume that on the right side of your tape, you have as many of these U's or blanks as you want. Not always at the beginning you might have a blank or not. So last time we assumed that we did to make it easier, but this time we'll assume no, you don't have that. But anyway, step 1. We'd say something like, oh. So if you're going through this Turing machine, what's the first thing you might do? You'd notice, okay, I have a 0 here. I'm going to have to cross it with something. For now, let's just cross it with an X. Then I'm going to have to go and look for a counterpart, a 1. Cross that with an X, right? Like for every 0, you're going to cross a 1. So that's the first thing we want to do here. So cross a 0 with an X, and then find a 1. And once we find that 1, we'll do the same thing and cross it with an X. Okay, then what? So with step 2, you have to kind of think about where your header is, because that's important. When we first started, my header was here. Cross it with an X. I kept going till I found a 1. Okay, I crossed this with an X. Right now, my header is currently here. So I know we want to keep going, and I want to cross this 0 and move forward. But before we could do that, I have to find that 0. So we'll say, go back to the start, or rewind to the start. Now, the start, we'll write it between quotations, because really, what is the start? It doesn't literally have to be at the beginning, but what we mean by start is I want to find the next element I want to cross. So say we find it, it's this 0. And make sure you're always crossing from left to right. Like I know technically I could go to this 0, cross it, then find a 1, but then it becomes a bit messy. Like you're crossing all over the place. Like always go back to the beginning, or like the first element, go there and then cross. So this 0 becomes an X, find a 1, X. So essentially what we did, we went back to the start, then we did step 1 again. And we're going to keep doing that. But this time, the next first element is a 1. No biggie. If you cross 1 first, then you'll simply go and find a 0. But this part is important. So like there's a kind of a symmetry here. Also, I could say, so or cross a 1 with an X, and then I'll find a 0 instead. Then find a 0 and we'll cross that here. So say we did that. When should we ever stop? So right now it's all X's. So when should I really stop and accept? Well, we just said it, it's all X's. You don't have anything else to cross. So if at any point it's just all X's, we'll accept. Otherwise, like say you're left with some 1 here that you never crossed, or some 0 and it doesn't have a counterpart, well, simply you're reject. So like you're checking your entire tape. Is it all X's? No, I'm left with a 1. Well, you're definitely, you don't know that it's the only 1. So what you're going to be doing is you're going to be crossing it with an X. Then you're going to go try and find a 0. You never find it. So that's when you really reject. You cross an element and you never find a counterpart. Okay, but remember what I said at the beginning where, okay, we could assume to the very right it's all blanks, but not necessarily at the beginning. So what we'll do is the very first element, we'll cross it with a blank, just so that marks at the beginning of our tape. So the first element, cross. So this is like a special case before we actually enter our loop. Cross first element, because it could be either a 0 or a 1. Cross that element with an X and find its counterpart or its opposite, whatever we're looking for. Okay, cool. And maybe one thing I should have added to the step 3, which is here. So if all X will accept, else go back to step 1. Like if it's not all X's, there's still some elements. I have to go back to step 1. And maybe before I have to go to step 1, I'm going to have to rewind again. Like the more detailed we are in our higher level description, the better when we actually draw the machine, the more accurate it's going to be. Now, remember what I said, you only have to cross the first element with a blank. When you find its other counterpart, like the first time, you don't want to cross that one with a blank too, because then where is your start? So just the first element you'll cross with a blank. When you find its counterpart, you just cross it with an X. So I'll say here, counterpart, cross with an X. Okay, so this is good enough. Let's now actually try and draw this machine. So remember, 3 things. We want to give a high-level description, we want to be able to draw, and we'll be able to understand. We just gave a high-level description. Let's now draw. And since there's some symmetry here, it's usually better to do it for one case or for one focus. Like let's say you're always crossing first the 0 and then finding a 1. We'll do that, and then we'll do this kind of symmetry for the red part, which is when you find a 1. So step 1, I'm at the start. This is the very first element, right? So I'll just, what is step 0 saying? Cross first element with an X. And we said we're going to assume right now it's zeros. So I find a 0. Let me actually just draw over here what we're doing again. So 0, 0, 1, 1, 1, and then 0, 0. Oh, just 1, 1, 0 at the end. Then blanks. Okay. So I find a 0. I'll write it over it with an X, and I'll move to the right. And nope, I don't want an X. I actually want a U, because step 0 says we want to mark the beginning of our tape. So here's a U. Cross this one with a U. So now we're always able to go back to the start. We're able to rewind. Again, if it's given to us that our tape starts with blanks, we don't need to do this part. Okay. Now what we should do, well, I want to find a 1. Okay, so I'm currently, my header is here. I have to keep looking until I find a 1. Once I find that 1, cross it with an X. So I keep skipping my 1s. So 1 and just move to the right. So, and if you don't want to overwrite something, you can just write it as the syntax. Like this is equivalent to as if I'm saying, oh, 1 overwrite it with 1 and keep moving. Like I don't want to change the 1, and whoops, again, I meant 0. I don't want to change the zeros currently. I just want to find a 1. So as long as there are zeros, we'll keep moving to the right. Okay, then what? Well, once I finally find that 1, we said we want to cross it with an X, move to the right. And now here, According to step 2, I want to go back to the start. So what I'm going to do is I'm actually going to go to that blank that we found. It's actually the real start. I like to call this state rewind. It's when you're going back all to some certain position. And it happens to be the start in this case. So now, no matter what you read, if you read a 1, go to the left. If you read a 0, go to the left. Even if you read into some X, you go to the left, like whatever. You keep going to the left until finally you read a blank, which means you're at the start, and you move to the right. So at this state, okay, I know that I'm at the start. Now, just one remark before we keep moving forward. When I crossed the 1 with an X, I decided to move to the right. So like my header's here. My header was here. I crossed it with an X, and I decided to move to the right. Now, two things. You could do that. Sometimes it might not cause problems, but there might be some extra cases you have to take care of. In this question, it might actually cause a problem that I'll talk about later. So the question is, should I move to the left or should I move to the right? It depends, of course, on the question. But usually, if you're rewinding, if like right now we crossed the 0, then we crossed the 1. So right now, I really want to go back to the start. So even though I could go to the right, I'll just say I want to move to the left. Kind of like I'm starting the rewind a bit early. Like I'm getting a head start on it. Cross a 1 with an X and like start moving to the left. Again, moving to the right might work in some cases. Here, I think it's going to cause a problem. But think about it like this, like you're getting a jump start on rewinding. Okay, like I was here, I crossed it with an X. Now I start going back until I find my blank. Okay, so now currently I rewind it all the way to the beginning. I'm at blank, then I move to the right. So really, I'm at this 0. What should I do? According to step 3, like I know I still have some 0s and X's I want to cross, but according to step 3, like you don't know that. You don't really have a vision of the tape. What you should do is check if it's all X's. If it is, we'll accept. So simply, at this point, check. Do I have just a bunch of X's, like X, and keep moving to the right? So like if it's all X's, and I find, like this is where you should accept really, like it's saying if it's all X's, accept. So if it's all X's, what does it mean it's all X's? Oh, you're able now to reach a blank, right? Like you checked the whole string, or the whole tape, it was all X's. You hit a blank at the right side, which means, oh, now it's empty. So we'll go simply to the accept state. So we'll call this Q accept, and it's instantaneous, it just stops. So we could call this state check all X's. Okay, great. Now what? Well, we are currently over here, if you remember, like there are no X's to check at this point. So it's not all X's, but it is a 0. So at this scenario, if I read a 0, what should I do? So there are two cases, like when you rewind it to the beginning, then you look for the next element, it's either going to be a 0 or a 1. Right now we're focusing on the zeros. So if I read a 0, it's obviously has to be replaced with an X. And like I move to the right. Like this is the very first element after the blank that has not been crossed. Just this one. So cross it with an X. And I move to the right. And I now want to find the other one. So I could actually make this one go. Where do you think this one's going to go? Over here. It's very similar to when we crossed the first 0 with a blank. Like we crossed the first 0 with a blank, then we tried to find a 1. Same thing here. Some 0 got crossed with an X. Now you want to look for a 1. So we cross it with an X. We over here. Now we want to find a 1. However, there's a problem. Currently, my header's here. All we have written is skip the zeros, but there might be some X's that you have to skip too, right? Like say you crossed a 0. Then you're skipping the zeros until you find the 1, but maybe on the way there are some X's from previous iterations that you need to skip too. So we'll skip those x's. Right, so like this one got skipped. Now my header is here. And we found another one. So this one will get crossed with an X. Now it's the same thing again, like this. Now I'll move backwards because we said, oh, cross one with an X, go to the left. We rewind all the way to the beginning. So all the way here. And let's just check a few things. Okay, so we crossed, as we said, we crossed one with an X. We rewind it to the start, so currently to this blank. Then we move to the right. So I'm currently at this 0. What do we do now? Well, we just crossed the 0 and 1, so we should check if it's all x's. So I skip this x, skip this x, skip this x. I'm now here at the 1. Makes sense? So now that I'm at the 1, we're kind of done with the zeros. Like we took care of all the possibilities for a 0. If it's at the very beginning, we replaced it with a blank, or if at some point I find another 0, I cross it with an X, and then I find the next one. So we're kind of done with the zeros. Now we should take care of the symmetrical part. We should take care of the ones. So two things. We're first going to do the blank part, then we'll do this part, which is what happens if you find a 1 that's not at the beginning. Okay. So I find a 0, or find a 1, place it with a blank, move to the right. Again, this is the scenario where, oh, what if at the beginning of your string it's a 1? Well, if it's a 1 and I cross it, I then want to find a 0. And it's symmetrical again to the beginning. So here I'm going to be skipping 1s. And maybe at some point there are some x's that I might need to skip too. Until finally I find a 1, or find a 0, cross it with an X, and same as before, just get a jump ahead on the rewind, move to the left. Now here is the question, should I make a whole other rewind state, and I rewind, etc., then when I'm done, I go and check all X's? I could do that, like I could literally do the symmetry and it might work, or I could make use of what I have written so far. I could say, oh, let's just go over this rewind, right? Like, because it's the same thing. I found a 1 and I crossed the 0. Now I'm going to rewind and check if it's all x's. Like, it doesn't matter if I cross 0 first or 1 first, because eventually I'm going to do the same thing. According to my algorithm, I'm going to rewind back to the beginning and then check if it's all x's. If it is, I accept. Otherwise, we go back. So say I rewinded. I checked if it's all x's. It's not. I happen to find this 1. So what do we do here? Where should we go? So I find a 1, cross it with an X, move to the right. Same thing as what we did above. It should go to the place that's going to try to find a 1 now. And I think this is probably it. So right now what happened? We crossed this 1 with an X. We went to find a 0. It's right next to us. Cross that one with an X. Then we move to the left. We rewind all the way. Check if it's all X's. It's going to say yes, and then we'll accept. Okay. So now I advise you to just maybe on a piece of paper or somewhere, rewrite this example and try to do it again from scratch. Like, go through the machine and see what's happening as you move. I think this is it. Like, you can never really know at this point, because the machines can get so complicated that you might be missing something, you might be forgetting something. So hopefully with practice, we'll be able to reduce the possibilities of mistakes. But hey, as long as it's like almost there, it's going to be good enough. Now remember what we said here, I don't want to put an R. Why do I want to do that? Well, think about it like this. Say I had this scenario, 0, 0, 0, 0, 1. Say this is your tape. Obviously, you don't want to accept this one, right? But look at the scenario. I might cross this with a blank according to what I said here. Then I skip all the zeros until I find a 1, which is right here. If I cross here with an X, and I move to the right instead of to the left, what does this tell you? There's nothing, there's nothing to rewind. There's only a blank. My current header is here. So I read a blank, I move to the right, and there's infinitely many blanks on the right. Then I check if it's all X's. There's no X for me to move forward. Is there a blank? Yes, there is. So I move to the right, and I go to the accept state. So this is a scenario where, had I put an R here, it might have caused some problems. Okay? It might not always cause problems when you do this, but sometimes it might. So let me actually do this one again. So we'll just try it here. What happens if we put 1x right instead? So what happens if we did this one here? Check. So we'll say check 0, 0, 0, 1. What happens? It'll become a blank, and then we go over here. This becomes an X. Blank, blank. Accepted. When it shouldn't. Hopefully that's clear. Okay, good enough. Now, so again, what we did was we drew a machine, we gave a level description. There is technically the third one where if you're given a Turing machine, we should be able to understand it. We're not going to do that one here, even though in class, so maybe a spoiler at the end, at the end of the class this week, I did resolve this question that we did online, where we were given a machine and we want to now be able to understand it. I'm not going to resolve it here because in Recitation 8, in the recording we did, so make sure you revise that one for the third idea, which is when should I draw, or how to understand a machine that's drawn for you. Instead, what I'm going to be focusing on is decidability, which is another big idea in here. So what is decidability? Some languages are decidable, and a decidable language means there exists some Turing machine that is a decider for this language, or that decides this language. So it's either a decider or that decides, etc. But what that means is you have some Turing machine M. It's going to take some input. It doesn't have to be a string or some tape, but let's say it is. Say it's some string W. And since this Turing machine, let's call it TM1, that decides L. It'll be able to correctly tell you, yes, if the string W will be accepted, should be accepted by L, and no otherwise. That's a decider. It'll be correctly able to tell you yes or no, always, which might seem weird because like this was always the case before, right? Like with PDAs, with DFAs, it was always gonna either say yes, the string is accepted or rejected. So what's new here? Why is this special? Well, since Turing machines are stronger there is some room for error. There is a possibility where you have a Turing machine that keeps looping forever and it never outputs a yes or a no, for example. That might be possible. Or you might have this, so or like there is another definition, which is a recognizer. A recognizer is a Turing machine that will be able to correctly tell you yes if the string should be accepted. So this is a recognizer. Again, what it means, say you have a language and you're testing out a string W, and you know that W should be accepted by the language. A recognizer will tell you, yes, it is. So there's no problem here. The problem is with the no. A recognizer might be able to say no, might not be. So there's always the possibility that the recognizer might loop forever, might be stuck, etc. Okay, so the complement L is decidable. Now, to solve these problems, I like to think of them or compare them to DFAs and NFAs and regularity. Like in this part, they're saying you're given L and L prime are decidable. Can you prove that this is decidable? If we were talking about DFAs, so if we were talking about DFAs and like regular languages, how would we have done that? Well, simply, I'm not saying tell me the lemma. The lemma says if you have a DFA that's regular, the complement is also regular. But that's not a proof. That's just using the lemma. I'm saying why is the lemma? Why is this property true? Well, let's kind of look at the proof of it. If you have a DFA that's regular, like L, say the machine M is regular for the language L. That means, again, L is regular, so you have some machine M for L, and it's regular. It's just a DFA, right? If a language is regular, it means it has a DFA. All we're saying is now, to get the complement, what we'll do is we'll flip the non-accepting and accepting states. So now these non-accepting before will be accepting, and the accepting will be non-accepting. So essentially we flip accepting and non-accepting states. That's how we get, that's kind of an intuition on the proof, right? Why is, if L is regular, the complement is regular? Well, it's because of this. If you simply flip the accepting and non-accepting states, you'll get the opposite language. Because you'll reject when the first language accepted, and you'll accept when the first language rejected. Okay. Very similar. Okay. So it's very similar to this proof, but the difference is what? It's not only now non-accepting and accepting. Now what we have is something like this. We have accepting, we have rejecting, and we also have like other states that are just going through the motions. So is it enough to say I just flip the accepting and rejecting states? So I say, okay, like here this was accepting, so now it's rejecting, and here it was rejecting, so now it's accepting. Is this enough? And then you have some other states. Not really, because usually there's something we say with Turing machines. Any non-existing transitions go to the rejecting state. What do I mean by that? Say you have say your alphabet, for example, is just 0, 1, 2. So 0 goes here, maybe on 1, 2. This one goes here on 2, etc. Some combination. What about the other transitions? Like your alphabet is 0, 1, 2. What about everything else? Well, there's something that we say. Any states that, any transitions that are not there, it's as if they go to the rejecting state. Like for this state, I don't have a 2 coming out. It's as if it goes to the rejecting state. Here, I don't have, say, 1 or 2. It's as if they also go there, even though they're not there. So if we only flip the Q accept and the Q reject, that's not enough. Because, okay, say 0, 1, say 2 here. Okay. Why is it not enough? Because before, okay, before 0, 1 went to the accept, now here 0, 1 go to the reject. Great, it got flipped. But what about the 2? Before, the 2 used to go to Q reject, and here 2, it's also gonna go to Q reject. Because we didn't do anything about it. It's a transition that's not there, so by default, oh, if it's not there, it should go to the reject. And that's wrong. So what we should say is not only flip, okay, so not only, give me some text, the Q accept and Q reject, but also if there are any missing transitions from the first machine in the new Turing machine, those transitions will go to the accepting state or to Q accept. Makes sense? So this too, instead of saying, oh, all the transitions go to reject, we're physically gonna say, no, this too should be added and going to now to the accepting. Okay. Hopefully that made sense. Okay, what about the other part? The union should be decidable. Now, this is actually quite interesting. Again, let's just compare it with before. So if we're talking about, say, NFA this time, and also regularity, could be also at DFA, that's fine. What we do is, okay, simply you'd have a machine for the first language, you'd have a machine for the second language, like this is for L, for L prime, and oh, I'd make a new start that go, and then epsilon that goes to the start of the first one, epsilon that goes to the start of the other one, which is great. But can I do that here? So can we do this for Turing machines? Well, yes and no. It turns out there are multiple types of Turing machines as well. Just like you have a DFA and an NFA, so you have deterministic and non-deterministic, you also have deterministic Turing machines and non-deterministic Turing machines. Everything we've done so far is technically can be considered a deterministic Turing machines because we never at some point said that, oh, if I read a 0, I write a 1 and move to the right, or if I read a 0, I write a 2 and I move to the right. That would make it non-deterministic. And we never had that. And technically, they could be equivalent. Just like a DFA is equivalent to an NFA, these two are also equivalent. But without worrying about this too much. So if we assume that we have this non-deterministic feature, essentially an easy way out would be, okay, you'd have like two tapes. The same tape, you'd have it twice. One would be running on the first machine. One would be running on the second machine, kind of like in parallel. And if one accepts, you'll accept. And this whole thing will be like one big machine Turing machine 3 that decides the union. So that's the easy way out. But say we didn't have that. So this would work. But say we didn't have that non-determinism. So what if it was a deterministic Turing machine? Well, that'll also work. So you could pause here and try to think of a scenario, like how could you make that work? Because there's no one unique solution, but it is interesting that it could work. So the idea is something like this. Now, you only have like one tape, right? So imagine, okay, we have the machine, Turing machine 1 for the first language, and you'd have Turing machine 2 for the other language. And I only have one tape that I want to run through them. So if I run it through the first one and it accepts, then great, I stop. It's over. I don't have to do anything else. But if it rejects, instead of making this a reject state, I'll change it to just a normal state and have this state go to like the start of the other machine. And then if this machine accepts, great, you simply accept. If it rejects, that means it's like both of them rejected, so neither will accept. The problem with this is, however, if you have a tape that's made up of some elements and you run it through the first machine is going to modify it and change it. So your tape is ruined. You can't really run it again to the other Turing machine. Now, somebody in class suggested that, hey, why not run it through a K-tape machine? And since they're equivalent, does it work? Yeah, that might be a solution, but I really want to do this with just one tape. So, well, simply what we could do is, remember, we're talking theory here, so really this tape is as big as you want it to be. Like on the very right, you have just infinitely many blanks. Just copy it. You just copy the tape. Like it's gonna be finite, whatever elements you have. Copy them, and even if they're not finite, like you copy them, and make a separator in the middle. Like we could put a $sign, you could put a Z, you could put some symbol in the middle to separate two parts. And then this one, you go over here. Oh, this is 0. You look at this one, it's 1, and then you go over here. 1, you go over here. With the simple operations of copy, read, write, and move, you can do this copy. Like this could be an interesting question if you want to think about it. Make like this is a neat exercise. Just try to copy the elements of the tape to the end of the tape. Just to give you an idea, essentially what you do is you'd look here. Like this is 0, you'd make it an X. You'd go over here and write a 0. Then you go back, make this as a Y, then you go over here and write a 1. Then when you're done copying, you move to the left and then you reverse everything you did. You'll just make the Y a 0 again, you'll make the X, Y a 1 again, and the X you'll make it a 0 again, kind of like reflipping. So it's possible, you can do it. So this is what you'll technically do. First, you'll put this tape into a Turing machine we'll call TM copy that copies this tape to the same tape, it just doubles it. And then you'd run this one at the start of Turing machine 1. And if Turing machine 1 rejects, instead of rejecting, you'll feed it into Turing machine 2, but right before you feed it, you'll make sure that you move till you find a $sign. So as long as you keep moving to the right until you see the $sign, then you move to the right. Like we can call this move to second part of the tape. And it works as well. Now, which is better? Again, just a quick reading it again. First, we're copying the tape. Then with the first part of the tape, we're running on the Turing machine. If it accepts, great. If it rejects, instead of rejecting, we move to the second part of the tape that actually has a copy of the start of the whole beginning of the whole original tape. We go over there, then we feed that part to Turing machine 2. And if that one accepts, we accept. If it rejects, that means it doesn't belong to the union. Now, which is better? Is this one better or is this one better? Depends, right? Like obviously the first one is more optimal because it's gonna run faster, right? But if I don't care about speed, which one is technically better? In this scenario, it doesn't make a difference. Since both machines are decidable, that means both machines will halt. Both machines will stop at some point and either say yes or no. However, say one of them was not a decider, was, for example, a recognizer. So it's possible, like say Turing Machine 1 was a recognizer. It's possible, and Turing Machine 2 would have accepted. So I'm saying you get some string W that might have looped forever in Turing Machine 1, but gets accepted in Turing Machine 2. If this happens, and you built your machine like this, you're always going to be stuck at Turing Machine 1. You never reach Turing Machine 2, so you never accept, even though you should. Whereas here, if it had looped in the first machine, well, the other machine will accept it and you'll simply stop. Now there's a possibility, hey, what if both of them are deciders and both of them will loop? Then neither route will work. So there's always that scenario. But the first one is safer. Like there are some cases that will work here, but won't work here. But it's still interesting to try and understand what we did in this part. Okay. Moving on. So this is the last part of this decidability. There's always more and more decidable questions that we could solve, just like the first part of the course. There's always so many pumping lemma, so many CFGs, so many PDAs that we could solve. So of course, the recitations are only the beginning. They're to get the ball rolling. You're going to have to try and solve as many questions as you can in your free time. Now, everything we've done so far with the decidability, it feels like it's abstract, and it is abstract, but technically you can write this down in English. Like if you were told to give a proof for this, you could either write it in English or you could do a drawing like we did if they're talking in the abstract sense, or both together, etc. Now, in this part, we're also going to be doing some abstraction, and maybe next time we'll actually write a proof in a proper way. So in this part that we'll see next time, we won't do in this time, we'll see an actual proof on how to write it. For now, let's do some more abstraction. So here with part A. EQ, DFA, RE. Okay. So what are we going to be doing here? It's also abstraction, but it's a bit more concrete than before. So we want to show that the following languages are decidable. So for example, this first language, EQ, DFA, RE, it's a machine that takes as an input D and R. D is a DFA, R is a regex, and the languages are the same. So essentially, if this machine is decidable, that means there exists, or if this language is decidable, there's some machine that takes as input D as a DFA, R as a regex, and it'll be correctly able to say yes or no. So it'll say yes if the language of this DFA and the language of this regex is the same. No otherwise. Cool. So this is what we want to prove. We're going to be able to do this. Now, it's like building Legos. In order to prove this, we're going to have to assume some things. Like, we're going to have to assume the following. Like, these are actually, I think you proved them in your course, in your actual book and class. EQ, DFA. Like, let's say these two are given. Given EQ, DFA and EQ. EQ, no, my bad. EQDFA and a CFG, it's given that they are decidable. What does that mean? It means you have a machine that accepts these two languages. Now, in case you're not familiar, EQDFA is simply the machine that takes DFAA as input DFA-B as input, so it's taking two DFAs, and it'll tell you yes if they are the same, so same language, no otherwise. So we're noticing that input doesn't always have to be like literally a string. It could be an entire DFAs, which is technically like a program, right? Like the description of a DFA. So yes, if the languages are the same, no otherwise. So we want to use this to build the bigger machine. Now to do that, very simple. In the very beginning, in the middle, as a building block, you want to use some machine. That machine will take some input. It's gonna give you an output of either yes or a no. Okay, so that's like the machine in the middle. And outside, you want to build a bigger machine that'll also take some input. And it's gonna also say either yes or no. So let's see this in action. Now remember, you see this blue part here with the D and the rejects? This is what we're trying to reach. So this technically will be the orange part. In the middle is what you have as given that you're going to be using as building blocks. So in this scenario, I'm telling you we want to use EQDFA. So EQDFA, what does it say? I'll take a DFA A, DFA B, and we're saying yes if they have the same language. How could I use this to solve the bigger problem? What's the bigger problem? It's this. The bigger problem says I'm taking as input some DFA-D and some rejects R. Now, one of those inputs seems straightforward, like DFA-D, I can just plug it in right here. The A is just arbitrary, like we're saying, oh, A equals D. But what about the rejects? I can't plug it in right into this. Like I can't put a USB A in a USB C. So I have to change it to something that can be inputted here. Simply, we could say, create a DFA C such that the language of C equals the language of R. Don't you think we can do that? Like if I give you some rejects, A star, B star, you could do a DFA for that. You could create a DFA for that. So whatever rejects you're given, you can make a DFA for it. And then this DFA that you created, you'll plug it in here. Make sense? Now you're checking if D and C are the same. But however, so say that says yes. If that tells you yes, that means the language of A equals the language of B. But the language of A is D, and the language of C is equivalent to the language of R. So that means yes, the language of D equals the language of R. Do you see that? One more time. I'm taking as input D and R. Okay. Taking it as input D and R. D, straight away we plug it in. The machine, so there's some machine, call it for example M, that decides EQDFA, which takes two DFAs and will tell you yes if they're the same or not. So DFA-D, I'm putting it as the first input for this machine that we know is decidable. Like this blue part, we know it's decidable. Like it'll be able to correctly tell you yes or no if two DFAs have the same language. Now the first DFA you're plugging in is just D. The second DFA you're plugging is a one that you made called C, where the language of C equals the language of your rejects. If the blue machine tells you yes, these two languages are the same, well the first language is, so this A is the same as this D, we just plugged it in the same, and this B is just a C, which is just the same language as R. So if this says yes, then your orange machine will also say yes. And if it says no, your machine will also say no. Like, no, their languages are not the same, so yeah, the other one's not the same. Does it make sense what we're doing here? Using the blue part, which we know is decidable, we were able to build this bigger machine that is also decidable because we just made a Turing machine. Okay, so that's this part. Hopefully it made sense. Okay. So now we're going to be doing the same thing, but now for this other part. Like usually this is a common idea that gets repeated, just like bumping lemma. There's at some point, once we understand it enough, it's just repetition. So same thing here. We're going to be given like, oh, say ACFG is decidable. What is ACFG? It's the machine that, given some context grammar G and some string W, it'll tell you yes if G generates W. Like if you're able to create the string W using G, it'll tell you yes. Otherwise, it'll say no. So this is given to you, and we'll just write it right here. Say M decides ACFG. The reason I write it like this, because ACFG is not the actual machine, it's just the language. And M is just some machine that decides it. And what does M take? Well, CFG, G, and some string W. You can pause here and see if you can fill the rest of this puzzle. Okay, but what does the big machine take as input? Well, just some CFG, G. According to the description, it's just one input, CFG, G. And it's gonna say yes if G generates epsilon. So it's like a specific use case of of this more general language. With the blue part, we're saying, oh, give me a string W, I'll be able to tell you if G generates it. Whereas here we're saying, give me just the grammar G, I'll be able to tell you if it generates epsilon and no otherwise. Which is interesting. Now, unlike before, where we were taking two inputs like DFA-D and regex R, and we plug in them into also two inputs, here we only have one input, but it's like needs to be split into two inputs. Not maybe actually split. Like, okay, this is just like before, straightforward. Or yeah, let's just write it. G gets plugged into G. And again, it doesn't have to be the same G, like G is arbitrary. Just like, so we're saying this G equals G, but they don't have to be the same. What about epsilon? Where does it come from? Well, it's a specific string. Just like if you were able to create a DFA, it shouldn't be a big deal to just plug in a specific string epsilon, which is just the empty string. So now what's happening? You're given some CFGG. You plug it in, and then you also plug in epsilon. The blue machine is going to tell you yes if G accepts W, but this W happens to be, so yes if G generates W, but this G is the one from the original input, and this W just happens to be the specific epsilon. Okay, so we're moving like this. And so, yes, it does accept it. Now, the final wiring, because we still have to say, oh, yes, it generates W, so we'll plug this in with saying, yes, G generates epsilon. And if it says no, we'll say no, because it's important. Sometimes you might actually flip the wiring in the opposite directions. In this case, we won't. Okay. One more. So part C, just say here this was B. Here we're doing part A. Now we'll do part C. Okay, how will we do part C? Well, take a moment to think what you need to use here. So all DFA, it also only takes one input, DFA A. It's gonna tell me yes. Okay. It's gonna tell me yes if A recognizes sigma star, or if in other words, it's the same language, like A just equals sigma star, no otherwise. What do you think we should use in the middle? So there are some other languages that might be given to you. But in this scenario, the two things we mentioned given at the beginning, they're enough, either EQDFA or ACFG. Obviously, since we're working with DFAs, what we'd want to use is EQDFA. Okay, we take input DFA A, and here DFA B. Again, it doesn't have to be the same A as the outside. Okay. Like if it's confusing why they're not the same A, like imagine you have some function f of x is 2x plus 3, and some other function f of x is like 3x. Just because both functions are in terms of x, it doesn't mean they're the same x. Like I could have written this one, f of y is 3y. Like these two are the same, right? Just like different arbitrary variable. These two are not the same, and this x doesn't have to be the same as this x. Like even this x doesn't have to be the same as this y. It's the same range, but like in terms of specific values, like at some I could input here x is 3, I could input here y is 4. Doesn't have to be the same. Okay, that's gonna be a mess to erase. Okay, but are you thinking of the problem, what we should be doing? Okay. Like here you could have put something like C or Y, whatever. And like when we plug this in, because it seems like we're gonna want to plug it in like we've been doing, we're just saying, oh, this C, we're gonna put inside of it whatever we're taking in as A. Or like some other A that doesn't have to be the same, we're just gonna be putting inside of it the A coming from outside. Okay. Well, I already said the first part. This A just gonna be plugged in right here. Let me actually use a different color so it doesn't seem like, so it's like different, right? Like, oh, we're getting this as input and we're deciding to put it here. But what about DFAB? What could we put here? Well, we want to, what does DFA QDFA does? It compares to DFAs. What do you really want to compare DFA with? You want to compare it with sigma star. You want to compare it with everything, right? Because this is going to tell you yes if the language of A equals that of B. So A is now the A coming from outside. What about B? We want it to be everything. So simply we could say I keep saying simply. It doesn't have to be simple. The idea is create a DFAC or J, name it whatever you want, that accepts everything. Is it hard to make a DFA that does that? So it's simply this. Oh, this could be simply. It's just a DFA that accepts everything. Like no matter what you get, whether it's E1, E2, like whatever your alphabet is up to EN. Keep looping over yourself. Like assume this whole thing is like some sigma, your alphabet. If no matter what you take, you keep looping on the same state and accepting, well, that's a DFA that accepts everything. And just like before, we'll plug in the C right here. So if if A equals B, that means this A from the outside equals the language of C, which is everything. So yeah, that's just as if we're saying you accept everything. Otherwise, if no, we'll just say no. Okay. So we're gonna be leaving it here. There are some other questions, a lot more questions for decidability that you could use. It goes on the same flow, right, that we've done. So look at these questions and try at the very least to solve this one, like 4.12. And what does this question say? So we can read it together. Some machine A, or some language A, that takes as input M, it'll say yes if M doesn't accept any odd number of ones. So again, you have some machine, so we'll call this TM1. It takes as input some DFAM. It'll be able to tell you yes if M does not accept strings that have an odd number of ones. So like strings where the number of ones is odd. Does not accept strings where the number of ones is ones. Okay, so make sure you think about that one for next time. And if you want, you can also think about the other questions. As a reminder that at this point, we also went over this third idea of Turing machines where we're able to understand something that's given to us. So like, even though this is a big question and it feels like it's kind of intimidating, if we break it down in just small parts, like it can be solvable. So make sure you check that one out from Recitation 8. And I'll see you in the next one. Goodbye.